Hi there, this is Jacob Nash Engineering Lessons in 1.3 Lesson 2. This is on the thermodynamics problems, and this is the... oh, sorry about that, I just dropped something. The first kind of problem you might deal with on a test or quiz for this unit. Now, in this case, we're going to try to find the final temperature. And we'll have to use what we know about the equations to determine this. Now, let's first read the problem and try to figure out what it's asking. So, a 3.80 kg piece of aluminum metal at 76 degrees Celsius is placed in an 8 kilogram glass of water, I guess. It doesn't say that. At 32 degrees Celsius. Now, here's a hint. I don't know what kind of assignments you might receive in your class. This is a problem created by PLTW, just different numbers. So if you understand how to solve this, then it will apply to what you have to do. Now, determine the final temperature, TF. So, what PLTW says to do is to first list all the known values in a problem like this. So, what things do we know? Well, first we have two components, aluminum and water, and the final temperature is just going to be what point they reach at the same time. So, basically, we're going to use an equation where they equal each other. So first, for aluminum, we can use Al. Now, you could use a lowercase l. I'm going to do uppercase just for this sake so that you can tell that's not an I. There's three things we can find. So, if I figure out how to pause this recorder, I'll do that next time so that you don't have to see me writing all this. So, MAL, CAL, oh great, it looks like delta, not that. And then TAL. Now, first, before we even try to figure out where these things came from, let's try to, I'm going to explain where I got these things from. So, we are trying to look for the temperature, final temperature. Now, how we can do this is by using one of the equations. But if you notice, none of those four equations I gave you on the last video have T is the thing that equals something. So we're going to use this equation, Q equals M times C times delta T. I gave you a little jingle for that the last video. Oh, this thing's starting to mess up. Okay, now we have this. But if you notice, all the components of that equation are trying to be found here. And I know we're not trying to find Q, we're not trying to find the energy transfer, but if we can figure out what the energy transfer is, then we'll be able to find the temperature and do it that way. So then we also have water, that's the other component, and then actually I'll just do it the same order as we did last time. MW, and if you don't understand what that means, it's saying the mass of aluminum, MAL, the mass of water, MW. Then CW, which is the specific heat capacity of water, and then TW, which is the temperature of the water. So first, what is the can we figure out what the mass of aluminum is? Is it told? Yes, right here. So I'll just say 3.8 kilograms. Now, secondly, do we know the mass of water? Is it said? Is it stated? Yes, right there. 8 kilograms. Next, do we know the specific heat capacity of aluminum? And then right there, you'd be like, no, what in the world? So it's not actually stated. Sometimes it will be stated. Hopefully your teacher will tell you what it is, but you can look it up. So of aluminum, the specific heat capacity is 900. Remember, there's no units for this, so it's just going to be 900. Then I already said this in the other video. The specific heat capacity of water is 4,184. Oops. Then, do we know the temperature of the aluminum? It's heated at 76 degrees Celsius. Then, do we know the temperature of the water? Yes, 32 degrees Celsius. So, we found out everything there. Now, what can we do next? We stated everything we knew. What don't we know? Really, the only thing we don't know is the final temperature, because that's what we're trying to find. And then you might also say, we don't know what Q is either. Well, the law of thermodynamics in the case of this problem would mean that the energy transfer of aluminum would equal that of the water. We'll explain more about that in a different video, why that's the case. But knowing that, we can now solve. So we don't really need to know what Q is to solve this problem, because Q of aluminum is going to be it's going to be the MAL. So this plus this plus this, because that falls up with this equation up here. Then of the water, it's going to be the same thing, and they would equal each other. If the Q's equal each other, then all these components are going to also, when put together. So we can actually solve and plug in the M, C, and T. Now at first you're like, okay, well what about the delta? We're completely forgetting about that. Well, the delta T is something else that we can state. So the delta T is going to be the hot temperature TH minus CH, or sorry, TC. Oh, this thing keeps moving up. Then, so knowing that, we can say what the delta T of aluminum is and of water. So first, what is it of aluminum? Well, we need to either plug in something for TH or TC. Which one? Well, we know that energy flows from hot to cold. So since the 76 degrees Celsius is warmer, it's going to be the TH for hot temperature. So we're going to plug in 76 minus TC. We'll figure out later how we can determine what TC is. Then the delta T of water, the change in temperature of the water, this time it's the cold temperature, so we just leave it as TH minus 32 because of the 32 degrees Celsius. So now we can plug everything in. So let's bring this down here. We can first we need to plug in for M of aluminum, because aluminum's on the left side. That is 3.8. That's what's in red up there. Multiply that by the C of aluminum. That is 900. Multiply that by delta T. It's not just 76, it's 76 minus TC. Oops. This thing's frustrating. Okay. Then equals, now we need the M of water, because that's on the right side. That is 8. And I'm just saying the letters, not what they mean in this case. That means mass. Remember that. Then the C of water, we said that was 4,184. Then the delta T is 32, or sorry, it's not 32 by itself. It's TH minus 32. And really, since we're finding the final temperature, we don't need to put TC and TH because this is the variable we're finding. So we can put TF. I'll just go ahead and do that. Minus 32. Now, what do we do next? Well, we can't multiply all these things yet because this component still has a variable in it. So we can first multiply this and this. So let me get my calculator. 3.8 times 900. Oh, I actually did 90. 3.8 times 900 is 3,420. And then that is multiplied by 76 minus final temperature, EF. Then, oh, looks like 7F equals, then 8 times 4,184 is 33,472. Now, you think these numbers are big. Wait till we do Stefan's law, and you'll get like billions and trillions. And then that's multiplied by the final temperature minus 32. Once again, this thing's trying to make me write 7 instead of T. Cursor keeps just like shifting down and up. Sorry, that's taking a long time to write. Now what? You're like, okay, we can't multiply this by 76. We have to distribute. So I'm going to use a different color to show that. So remember, when you distribute, you multiply by each of those components. So we really are multiplying that, but we also have to multiply that. So now, once we've done that, 3,420 times 76 is, let's see, what is it? Oh, 259,220, or sorry, 920. And then that is going to be minus, because of this right here, and then that's going to be 3,420 TF when those are multiplied together. The variable just goes beside it because you can't do anything. Then this side, we multiply 33,472 times 32. Or no, we'll do this part first. So we'll just 33,472 TF when those are multiplied together. Then we have to do minus because of that, and then we get 1,071,104. Strange numbers, but it will get better. Now let's get the variables on the same side. So I like to do the smaller one so that it doesn't end up negative. So let's add this to both sides. I'm not going to write it out on both sides just for the sake of time. And once we do 33,472 TF plus 3,420 TF, we get, I'll just start writing over here now, you get 36,892 TF. Then we still have this part. We're going to want to add this onto this side. So once we add this 1,071,104 to 259,920, let's see what we get. Okay, now we get 331,024. Now the only thing left is to divide by this on both sides. I'm not going to write it out once again, but you divide 1,331,024 by 36. Well, other way around. You divide it's this over this, and type that in. We get that the final temperature is 36.7 or 07. Actually, it would round to 08. Sorry. And is that the answer? No. Have to have a unit. And what unit? Well, the one that we were given. If the problem had Fahrenheit, we would use that, but since it has Celsius, we'll do that. Degrees Celsius, and that would be the answer. And yes, that is the end, if you were hoping for that. And I know that was a lot of work, but once you get the hang of it, it will be pretty simple for you to do. And I know this video was super long, and it was only because I don't know how to pause on this thing. I'll try to figure it out. This video probably only would have been like 10 minutes if I did that. Because the screen recorder I used on the past 2 units, I was able to pause. That's why the videos are longer on this one so far. But that is maybe the most complicated of these 4 problems in this next series of videos that you'll have to deal with. The next one will be on thermal conductivity. It is definitely not as complicated because the equation is a lot simpler. Then R value, that's simple. That will be lesson 4. I mean, then lesson 5 will be Stefan's law. That one may be a long one as well, but as long as you get the hang of it, you'll be fine. So this is one of the 4 problems that you'll deal with in thermodynamics, and if you understand it, great. And thanks for watching. I'll see you next time.